be explaining some basic data science using dice. So I had this idea a while ago to use dice to recreate an image. Now, I don't know if you ever tried to do that, but it's not exactly something you just do. So, you needed to do some things. First thing I needed to do, I need to figure out what my end result was. Dice. What does that mean? I want to define a die as white cube with black dots. Pretty easy. One side is showing at a time. Imagine on like a canvas, just one showing at a time. 2, I need to define how many states I could have as my end product. In this case, die has 6 sides, 6 states. Bada bing, bada boom. Pretty easy. 3, I needed to get there. That's the hard part, and that's the purpose of this video. I'm going to be explaining how we get from pixel values to sides of a die. And you can see already I've done it, but we're going to go back to, that was a weak snap, color. Because I'm going to go through this step by step. I'm going to show you what each thing does. So the first problem we have is that a die doesn't have colors exactly. It has a brightness, in a sense, where having 1 dot is as bright as it can be, and having 6 is as dark as it can be. So first off, this will not be a color image. So first thing we're going to do, knock out color. Now we have, this is called grayscale. Essentially, instead of having a red, green, and a blue value for each pixel, we now just have what's called a W value, and that's the white. So this value can range anywhere between 0 and 255. So I'm going to keep in the top left what we know about our current data, and also have a little bit of sample data here to follow along with. So, we know we had 3 channels, red, green, and blue, and now we only have 1, our W channel. We are in grayscale. All we know now is that our data will always be between 0 and 255. The next step would be, we need more information. We need to know the minimum. So, what we do is we subtract the minimum value of all the pixels. So if the darkest pixel is, I don't know, say at 16, we subtract 16 from everything. Then, what we know is that the minimum value of the entire frame will always be 0. So I'll do that weak again. Now, so that's called a reduction. We've subtracted a uniform value from every frame. So, now we know we are somewhere in between 0 and 255, and our minimum will always be 0. What we do next is we do something called normalization, where we divide this entire set by the maximum value, meaning if the highest number is, I don't know, 155, we divide every value of the frame by 155. Now what we know is that the minimum is 0 and the maximum is 1, meaning the darkest part of the image will be absolute black and the brightest part of the image will be absolute white. So we'll do that now. So now we have what's called a normalized set of data, something between 0 and 1. This is pretty standard in data science. So what we need to do next is we need to somehow get this into the states of a cube. So we know a cube has 6 independent states. So now that we have numbers between 0 and 1, we can represent those numbers as a state. So what we do to do that is we multiply it by 5, not 6. We multiply it by 5 because 0 is included. So if we are at the brightest pixel and we know it's a 1, we will now be at, what's it called? Right, if we multiply it by 5, we are at 5. if we were at the darkest part of the image and it started as a 0 and multiplied by 5, we're at 0. So we actually do have 6 states, it's just we only multiply by 5. We have 0, 1, 2, 3, 4, and 5. So yeah, that's that. So now we are in one of 6 states. Oh, forgot to mention, we round as well. So because multiplying by 6 doesn't really, or 5, sorry, because multiplying by 5 doesn't do anything on its own, we need to put it into discrete states. See, a continuous state means we have a decimal point, essentially. It can go on forever and ever, being represented in infinite ways. We need to make sure this is represented in one of 6 ways. So once we multiply by 5, we round. So every element of every pixel of this new frame will be rounded to the nearest one. So that's what this looks like. So now, every color you're seeing right now is one of 6 on the entire screen. So, what we do next is, now that we have something between 0 and 5, we need to think about how this gets mapped to a die. So, with a die, when you increase the number of dots, we decrease the... Parents are watching The Office. Awesome. We know as the number of dots increases on a die, the brightness decreases. So we have a representation for each pixel now between 0 and 5. We can do, so we know 0 should be the darkest. The darkest state of a die is 6 dots. So what we actually need to do is we need to basically start at 6 and work backwards from whatever number each pixel is in. So once we do that, we know how many dots we should have on each die. And then essentially, we're back where we started. Weak again. There it is. So now, this is what it looks like. Now each die here is a 5 by 5 representation of the die, so it doesn't actually look all that great, especially if you're not watching this video in a high resolution. So, also I came up with another little equation here that can set the maximum number of dice that can be used to represent, because I was originally going to do this to actually, I was going to try to actually get like 5,000 dice and make like a little portrait of my dog out of them, this picture, but that'll have to wait. It's kind of hard to get 6,000 or 5,000 dice as you would imagine. But basically, here we are. Now we have independently taken our, not continuous, but we do have a discrete 0 to 255 value now scaled down into a discrete 0 through 5, or 1 to 6. You can just add 1 and call it 1 to 6. And that's essentially that. So, what I want to talk about is... I lost my train of thought. Oh yeah, so what I want to talk about is what is considered transformation. So every step there was a transformation. The reduction, the normalization, the multiplication, the rounding, those are all called transformations, and they all happen to a set of data. See, you can represent every pixel on the screen as a single list of numbers, and as such, you can do a transformation on an entire set. So the definition of a translation, the definition of a translation is to, essentially what you want to do is modify an entire set of data, that entire list, by some uniform property that will essentially get it closer to some goal. This is used in neural networks a lot because it's hard to explain why, but essentially having a number between 0 and 1 is a lot easier to keep control of in a neural network than 0 to 255, especially when the number isn't 255. See, most conventional cameras, including the one I'm using, do keep their pixel values between 0 and 255, but there are much higher quality and lower quality cameras that can range from as low as 2 colors, usually around 8 colors, all the way up to 10-bit, which is, what's that? That's going to be 256, 1024 colors per pixel. 0 to 1024. That can happen. So what this normalization does is it allows us to convert between these. And you can't always just kind of create data, so I can't start at something that has 6 possibilities and get back up to the full 0 to 255, because that data just doesn't exist. But I can represent it that way. So if I needed to, say, submit a file to something that was in, it's called 8-bit color, that's up to 255, that's 0 to 255 for pixel values. But say I started with one that only had 6 possibilities. I can't submit that file with 6 possibilities, it just won't work. So I can do this entire thing essentially in reverse. Divide each, if it goes 0 to 6, I can divide the entire thing by 6, I can then multiply it by 255, and round, because it needs to be an integer, and then I have that file. And it's just very important to realize you are always doing the same thing to every element of this list. Now, this list always isn't always linear. It can have multiple dimensions. There can be tens of thousands of dimensions to this data, which is very hard to imagine, but it's real. Let me get some water. But yeah, that's essentially data transformations and how they work. This is a very nice example. I think it very well encapsulates what data transformations can do, and I think it looks awesome. So yeah, here we are. See y'all.